In this topic, we'll discuss overplotting, one of my favorite topics here. Here's the premise. Your descriptive analyses have revealed that your fast food restaurant has received more and more customers over the years. To demonstrate this finding, an analyst at your company makes the below visualization. While it is visually appealing, you don't think this clearly communicates the finding. Are you being misled? And so here you can see that we have data again in a Parquet file. We read that in. We're actually just focusing on one column of that data frame. And so we extract that series and we go ahead and create our visualization. Let's go ahead and take a look. And so here you can see that we have a lot of time series data. And in this time series data, things actually get quite messy. Now we've tried to clean up the x-axis as much as possible, only label the months, and we've performed what is commonly referred to as a year-over-year analysis. And now maybe I might look at the average for each month to have a better look at this, but can you make heads or tails of any of this data? Am I being misled? Here's a hint. If you're not sure if you're ever being misled, think about what the graph is telling you, or what the author is telling you. The author here is using the title to tell us that daily customers increase across the years. So I should expect to see some type of signal that from 2000 to 2010, we have an average increase in the number of customers. If that message was not part of the title, would I ever be able to come to that same conclusion with this graphic alone? And here is the answer. No, you would not have come to that conclusion on your own. That graphic was massively overplotted. And what we can do to kind of avoid some of this overplotting, I'll share with you what I mean about overplotting. Overplotting is simply the representation of too much data on a single image. Now, there are so many different techniques that we can do to address this, but one thing that I will point your attention to is that our years are not a nominal scale. Our years have an inherent ordering to them. The year 2001 comes after the year 2000. The year 2002 comes after the year 2001. Yet, we are using a categorical color palette to represent my yearly data. And so this might not be the best choice here. If I want to communicate something about change across the years, well, maybe I should have a little bit better usage of my X and Y axes here. Maybe I should have just aggregated and just reported averages. Shy away from just reporting averages. Always try and include, right, as much context as you can in your visualizations, but the smoking gun here is the use of a qualitative color palette for data that is qualitative but ordered. And so what we can use instead of a categorical color palette is we can use a continuous color palette downsampled to the number of categories that we have. And what this means is I'm going to take a color palette that goes logically from one color into another color, and then I'm going to sample evenly along that space up to the number of years that I have. And you'll start to see a very interesting effect. You can see that my colors start at a kind of a deep purple in the year 2000 and turn into green in the mid years, and then finally turn into a yellow. This is the Viridis color map. You can also use something like blues or any linear sequential color palette. But the very interesting part here is that you can start to parse apart these individual lines, but you can see the further up this graphic you go, the more yellow the lines become. That is the relationship between year and our number of customers. And so if we were just to look at the colors and ignore the jaggedness of the lines, we can start to see some of that relationship. But I still wouldn't even say that this is the best way to represent this data because there's still just way too much going on. One of my favorite tricks is the use of small multiples. And in order to explain this appropriately, I want to just mention that the perceptual cues for those ordinal and nominal scales are different, right? What I'm trying to convey here is that our ordinal scale can actually exist on a linear or sequential monotonic scale, whereas our nominal scales are always independent and categorical, and that's where we would want something like a categorical color palette. And so there are many different color palettes to choose from when you're trying to visualize your data, and it's very important that you use appropriate color palettes. They'll be sequential, they'll be diverging, they'll be categorical. So make sure you choose the color palette that most accurately represents your data. But here is the power of small multiples. Instead of one plot, I'm going to be making many. In fact, I'm going to make as many plots as I have unique years in my data. And I can then group over my data and actually plot my data on all different plots. And when I do that, you'll notice just a little bit of a pattern. I'll actually go ahead and plot this for you. And you'll start to see absolutely nothing. There's nothing here that makes any sense at all. And the reason that is because small multiples, or the use of multiple small graphics, is only useful if every entry in your small multiples has the same x-axis and has the same y-axis. And this is going to be a perception that leverages the position across graphics. And so you'll see here, now that we share our x and share our y, you'll start to see a pattern over my small multiples. You can see on the top left-hand corner, the year 2000, the data start off very low on that y-axis. With each sequential year, we start to see that just the average, the horizontal position of my zigzagging line starts to increase. All the way into 2010, we can see that it's hugging the top of my y-axis. And you can see this trend across the graphics. This is the power of small multiples. When they actually share their x and y axes together, you can see trends that are not apparent when they are laid on top. This helps us reduce the overplotting that we're doing, and it also has your eye focus on the differences between the plots instead of the minute details in a single plot. So this is a great way of conveying a bigger picture idea. But we can add more. We can do even better. If you're ever doing small multiples of time series data and your data makes sense, I can actually plot the mean, right, the average for that full year, just as a horizontal line. And this will actually help direct my eye to those subtle jumps from year to year. And so you can see that my horizontal line keeps ticking up and up and up with every single year. But my favorite trick of small multiples is to provide context. And that context comes in the form of not just plotting the data for that year, but plotting the data for that year, and then in the background, plotting the data for every other year, just in a lighter color and a lighter alpha so it doesn't shine through as much. And so now if I look at a single plot, I can see how that plot, how that line in 2000 compares to the rest of the data. And this creates a very nice visual or perceptual trick where it feels like I can see each individual line just by looking at each of these graphics because I've overlaid the same kind of gray squiggles on every single plot. And you can start to make out the unique contribution that each year has towards my overall grand total of my numbers of customers or daily number of customers across the years. And so I love using this trick of small multiples. I think it's super powerful, especially when you have those charts that have, legends with like 20 entries in it, and it's just way too much information to communicate in just a single plot. I would very much encourage you to start thinking about using small multiples in your work so you can communicate more data, but also more effectively. But what other tricks do we have? Well, small multiples are very useful when we're talking about overplotting with line charts, as we've shown here. Not as useful when we're talking about scatter plots, though. If I were to redo this with different scatter plots, things get a little bit hairier. This is very, very useful for line charts, though, or for contiguous scatters. But scatter plots actually have their own inherent problem when it comes to overplotting. You can see here that I've just sampled some data, and I have about, I think, 1,000 or 2,000 data points on the top left-hand plot, as well as 1,000 or 2,000 data points on the top right-hand plot. What if I wanted to represent these two groups on the same plot, or on the same axes? What if these are two groups that I want to be able to compare positionally to one another? Well, the most obvious case would be simply just, well, why not plot them on the same plot, and let's see what happens. So let's go ahead, and now I've plotted the oranges with the blues on the bottom left, and you can see that there's a lot of oranges hugging the top, and there's a lot of blues, but that just looks kind of like a blobby kind of mess to me. I have no idea how much data there is actually within each of those blobs. And you saw that I've used a trick like creating the white edge colors in order to help figure out within a given blob, maybe help me visualize how many data points there are underlying that. But let's go ahead, and I'm going to make one more plot. Except in this plot, all I'm going to do is change the ordering. Before, you saw me put blue first and then orange on top, and now I'm going to put orange first and then blue on top. There's going to be a change in my data, or in the representation of it. All of a sudden, all of my blue scatter points are sitting on top of my orange scatter points, and this starts to tell a very different story. The lower left-hand plot that has the orange on top of the blue tells me that there's probably more orange points than blue, and orange occupies a much higher average than blue, whereas blue is very close to hugging the bottom of the axes. Whereas on the other side, now I think there's more blue points than there are orange, and maybe their respective means, I might not differentiate too much in their respective means and what that interprets to. So how can we fix this problem of overplotting? Because I very recently saw a very thorough analysis that concluded it's, big data is very hot right now. And so this problem of overplotting is all over big data analyses. You want to show all that context, all that data, and you're reduced to either vastly over aggregating or playing with some very funky tricks to try and show all that data that you want to. And so if you're ever working with huge data sets, I would recommend you try out these solutions, and then at the end, try out probably the best solution here. But the alpha solution, and I use this term loosely. By playing with the alpha of each of these scatter plots, I can actually start to see just a little bit more data here. And so I'll go ahead, let's keep the alpha full just so we have something to measure against. And so this is what full saturation looks like, or this is almost oversaturation. But if I just bump that down to half, alpha is now 0.5, we can start to see maybe a little bit more of those blue points existing under those orange points, but we still have this huge oversaturation problem. And oversaturation is whenever we have so many overlapping data points that we can't see the underlying ones, especially when it comes to trying to blend different colors. And so maybe 0.5 is just a little bit too high. Maybe I really need 0.1. And so I'll go ahead and I'll use 0.1 as the alpha value. Okay, my data clouds are starting to become, a little bit more disambiguated. I can see that there's a large amount of overlapping points, but orange and blue seems somewhat distinct. Maybe I need to bump it down even further, maybe to 0.05. And you can see that when I bump it down even further, okay, I can still see there's two distinct-ish clouds of data, but those points on the outskirts are actually just disappearing on me. They're completely going away. And maybe that's not the focus here because I just want to look at the densest points. But let's see if this alpha solution is actually effective. Let's plot the reverse. Let's plot orange on top of blue instead of blue on top of orange. And we see that we actually get some similar looking results. Now, these aren't the exact same. It looks like there's a little bit more blue over here than there is over here, but if you squint, these look pretty similar. So maybe alpha is a good thing to use. Well, if all you're doing is creating one visualization and you're done with it, you just want to look at it and you're done, you're not showing it to anyone else, I think alpha is a totally fine solution to use. Maybe a combination of alpha and our next trick, but if you're creating a programmatic data visualization, data viz creation pipeline, I would not rely on any alpha tricks. And that's because what you just saw me do is this small iteration loop, and this comes up all the time when you're creating data visualization. You select some values for that alpha level, you look at the plot, you say, is this good? No. Okay, I need to change it again. And then you look at it again, and you have to ask yourself, is it good? Do I need to change it? Do I keep going? We cannot represent this programmatically because we need that human intervention to answer the question, does this look good? And whenever you have to ask yourself that question when it comes to data visualization, that is a non-reproducible workflow, meaning you cannot program that, meaning that whatever visualization you create by tweaking those alpha values, you have to do that every single time. So that means if you just change the underlying data set, maybe to a similar data set but slightly different, well, you have to go back in, you have to reselect those alpha values, and then you might be sitting there trying to create a dictionary of data set sources to alpha values that look good, and there's no way to automate your life. So maybe we need to pick up our next trick. Maybe we just need a smaller point, right? The circles in the scatter plot were just quite large. And so let's go ahead and let's use a smaller point, and this is indicated by the S keyword argument in our scatter plots. And so I'll go ahead and plot that. Points. You can see that, well, it looks much better than before, and let's bump this back up. The default should be 20. Let's bump this up to 20. You can see it just looks like orange and blue blobs. I lower it down to 4, the size of each scatter point to 4. I start to see a little bit more granularity in my data. Maybe this size trick is what we need. Well, we can ask ourselves, what happens if I plot the reverse, orange on top of blue? Do I get a similar result? And you can see that, I don't get the same result. It's definitely similar, but it's definitely not the exact same. And if we're trying to create automated or reproducible workflows, it should look more similar than this. And so maybe we need to combine tricks here and say like an alpha of 0.5 with a size of 4. And we start to get a little bit similar values. Maybe we need to go back down to 0.1. And now we've created things that look almost indistinguishable from one another by using points or the size of each point as well as the alpha. But we still run into this problem of a non-reproducible workflow. And what this means is that if I ever want to automate the generation of this visualization, well, I'm going to have to sit there, make the visualization 5 different times with different sizes and different alphas just to see what looks good. Another approach we can take is sampling. We can actually sample our data points. And so if I were to do this, right, I would just use maybe a NumPy choice and specify a fraction of the data points that I'm trying to represent here, and then just downsample the amount of data points and just assume that, well, if I sample my own data set, it should carry forward all the characteristics, like the mean's going to be the same. Is that not enough? And you can see I don't have 2,000 data points to plot anymore. I just have 200. And we can start to see that these are very separate data clouds. Does this carry forward when I plot blue over orange? They do end up looking quite similar, but we've lost 90% of our data. We've only taken 10% of it. And so there could be points that are very important to the conclusions that we want to draw that we have just completely left out because we said, it's too much to represent. And while I think downsampling subsampling has its place, I don't think it's a great solution here. However, if you're looking for something that's automated, well, I can always take 10% of my data. That's very easy to program, whereas playing with the size and alpha are not easy to program. Another approach that we can take is actually the use of 2D histograms. A 2D histogram is very much like a 1D histogram, except instead of just binning one variable or one metric along an axis and creating bins and then counting the number of bins it falls into, you essentially create an X and Y axis, and then instead of creating bins, you're creating squares on a grid. And then you say how many scatterplot points fall into this bin. And so if I go ahead and I plot my 2D histogram, you can actually start to see a little bit of change here. The very important thing that I miss out on when I do this is I don't have any distinction as to what these two groups are. But the important part is that I can now finally tell how many data points there are in this data cloud, which is something I've been unable to do. And so if I really, really wanted to tell, I would actually need to save this metric back out, and then I would need to add a color bar that maps this qualitative or quantitative color information to an actual value. And this was my axes 1, 0. And so just by adding a color bar, let's go ahead and do that. And hist2d returns multiple things, so we just need to inspect those. Hist2d returns the bins and then the scalar mappable. There it is, the third thing. And then now we have our image, and now we attach our color bar. And so now we have our actual color bar, and I could do this individually for both of those to preserve that group level information. It spans this out to 2 plots, but I can finally tell you that, oh, in the center, in these very hot spots, the 2 hot spots, I can see that I have about 190 data points in this cloud. Whereas if you were to look at this top left scatter plot, would you ever be able to deduce that there's 190 data points just in this small square around between 0 and -2? Probably not. So let's see how else we can draw this 2D histogram. We can actually specify more bins. More bins is better, right? But you can see when I over-specify my bins, I now have 100 bins instead of just 10. And I actually lose some of the information about these data clouds. And not only do I lose information, but I start to lose the ability to draw information from this because the boxes are just too small for me to convey or understand anything meaningful. If you squint very hard, you can kind of see a cloud up here on the top and a cloud down here on the bottom with a little bit of a darker blue in the middle. But maybe I would want to do some smoothing to this 2D histogram just to make it a little bit more interpretable to show that there are in fact 2 separate data clouds here. Now, these are all tricks that you can use. You can use a hex bin plot, you can use a 2D histogram, but they're sidestepping the problem, and it's that when we have a scatter plot with too much data, how do we represent that without overwhelming our audience or our intended end user? Well, there is a fantastic Python package out there called Data Shader. And what Data Shader does is it performs local aggregations in order to convey points about large data clouds. It's one of those big data projects. And so if you're ever working with big data and you need to present your data visually in the form of a scatter plot, or maybe you're overlaying individual points onto maybe a geographical plot or geographical set of axes, Data Shader is going to be very, very beneficial to you because it uses a very intelligent algorithm in order to effectively aggregate your data at a very small scale so that it's perceptually noticeable, but you're also able to understand the amount of data within your clouds, within data clouds. But that is what I want to talk about for overplotting. Remember, there are so many different tricks that you can use, and I think an important distinguishing feature of these tricks is to ask yourself, do I need to make this plot many times over with different data sets? If your answer is no, go ahead, use alpha, use size. It's going to be quick, it's going to be easy. If you do need to make this visualization as part of an automated workflow, those tricks are not going to help you. You should reach for something like a 2D histogram, a 2D hex bin, which do have their own drawbacks, or use something more intelligent like Data Shader.